Let's take a few minutes here to introduce the idea of kinetic energy, and this is the energy that's related to motion. So first of all, this is, like I said, the kinetic energy that is the energy that's associated with the motion of an object. And these are the following properties of that kinetic energy, things to know about it in terms of physics. So like all energy systems and like energy in general, it is a scalar. The variable you will often see either Ke or capital K. In both cases, they're used pretty interchangeably. I think you'll most often see Ke. I think that's what the AP uses, but sometimes you'll see K. The units, like all energy, is in joules, which if you remember or you recall is a kilogram meters squared per second squared. And the equation for kinetic energy is that a change in the kinetic energy will be equal to 1/2 m times the change in the speed squared. So the constant, if you remember in the energy interaction model, there's always a constant times a change in an indicator. The constant in this case is 1/2 m, and the indicator is speed squared, or v squared. And it's important to note it is v squared, and then we find the difference. We don't find the difference and then square them. So as an example, how much kinetic energy is gained by a 60 kilogram sprinter increasing their speed from 3 meters per second to 4 meters per second? How about from 4 to 5? So we will find that delta Ke is equal to 1/2 times 60 kilograms times the change in speed squared. So that's going to be 4 meters per second squared. 4 meters per second quantity squared minus 3 meters per second squared. Because again, remember, it's going to be final speed minus initial speed, and in both cases they're squared because originally we had delta of v squared. We are changing the v squared. And if we plug that into our calculator, or we do this mentally, hopefully that will work out, 30 kilograms times 16 meters squared per second squared minus 9 meters squared per second squared. It's going to be 7, so that will equal 210 Newton meters, or kilogram meters, or kilogram meters squared per second squared, or joules. Let me go back and add that up here as well. 1 joule, which is equal to 1 kilogram meter per second squared, which is equal to 1 Newton times meters. If you're not sure about that, check in with me in class and we can talk about it. In any case, we see 210, the most common will be that 210 joules. So 210 joules. Now, if we look at changing from 4 to 5, we have to write the equation again. 1/2 60 kilograms times 5 meters per second squared minus 4 meters per second squared, and that will equal 30 kilograms times 25 meters per second squared minus 16 meters squared per second squared. Sorry, that was a mistake. This should both be meters squared per second squared. That will give us 30 times, what is that, 9, so that will be 270 joules. So you'll notice they do have the same change in speed, 1 meter per second, but they don't have the same change in squared speeds. And that points out here, they must be squared before they are subtracted. I know it's a little hard to read, but again, you do the squaring before you do the subtraction. So, as another question, here's what you'll see. How much kinetic energy is gained by a 1,000 kilogram car when it goes from rest to a speed of 15 meters per second? So again, delta Ke is equal to 1/2 1,000 kilograms times the final speed of 15 meters per second squared minus the initial speed of 0 meters per second squared because it was at rest. So that will be 15 squared, which is 125 if I'm not doing my math wrong. 15 times 10 would be, sorry, it should be 175. 15 times 10 would be 150. 15 times, or sorry, 5 times 5, 25. Yeah, so 175 times 1,000 would be 175, 1, 2, 3. Half of that would be, I don't know, whatever half of that is. It's late and my brain is a little bit fried, but you can plug that into your calculator and figure it out. Now, as we'll talk about with all, or as we talk about with all energy changes, we can only calculate technically changes, but sometimes you'll see kinetic energy expressed as an absolute value. So something will be like, oh, this car right here has this much KE. So rather than saying it's gained this much kinetic energy from rest, they'll just say this car has half of 175,000 joules of kinetic energy. Whenever you are just given an amount of kinetic energy, what they're implying is how much more kinetic energy the object has than when it was at rest. So they're doing this equation right here. Because again, properly we can only calculate changes, but because there's such a common reference point of at rest, sometimes we'll talk about something just having kinetic energy, because that's basically the kinetic energy we can free up if we bring it to rest. Or that's how much energy was required to get it up to that speed. So that's why we'll talk about it having a certain amount of kinetic energy, because that's how much was added when it was at rest to get it to that speed, or how much you can free up when you bring it back down to rest. So that's just a little technical point. If you have questions about it, let me know, but otherwise we'll move forward.